The last video for topic 7 is looking at Le Chatelier's principle. And so now we're looking at, well, how can we affect where equilibrium is going to lie? So definition. A system at equilibrium, when subjected to change, will respond in such a way as to minimize the effect of that change. So let's say we add something. So we're going to add some reactant to the reaction that is currently occurring. Well, the reaction is going to adjust to remove it. When it does that, you are going to get a new equilibrium. Now, these are a new equilibrium position. However, it doesn't actually change the value of Kc unless it is affected by temperature. It just changes those ratios that the concentrations at equilibrium are at. Now you can do this vice versa. Let's say you remove something, right? You're going to remove the product as it's being formed. Well, if you remove the product as it's being formed, we're going to want to add back to it to reach equilibrium. Therefore, once again, reaching a new equilibrium with new concentrations, but those concentrations are going to be in a ratio such as that the Kc is the same. Kc is only affected by temperature. So now we're going to look at different factors that can affect the equilibrium position. First, we're going to look at changes in the concentration and what effects that might have. So we're going to look at this sample reaction throughout a lot of these processes. So we're going to look at N2 gas plus 3 moles of H2 gas will produce 2 moles of NH3 gas, and it is an equilibrium reaction as denoted by the double-headed arrow. So if we add some H2, right? So H2 is a reactant, so we're adding a reactant. Well, as we add the reactant, the system wants to adjust for that, which means the system wants to remove it. So more of that reactant is going to become a product. Therefore, we're going to see more production of NH3. And that way allows it to re-equilibrate in order to remove the effect of that increase of that reactant. So let's say we're going to remove our product as it's being produced. So we are decreasing its concentration. Well, when that happens, we are going to favor products. Because we're decreasing the concentration of the product, we need to replace that decrease. Therefore, we're going to shift more of the reactants to the product side to try to re-equilibrate it, pushing the reaction in the forward direction. So once again, remove the product, add more product, right? Now, Kc remains unchanged in both cases because it's only affected by temperature. So now I just want to go through some examples. So let's say if we remove a reactant, right, what's going to happen? So if we're going to remove the reactant, we need to replace that reactant. So we are going to shift towards the reactants. If we remove a product, we want to replace that product. So we're going to shift towards the products. If we are going to add a reactant, we want to get rid of it. So we are going to shift towards products. If we add a product, we want to get rid of it. So we're going to shift back towards reactants. And so you always want to go in the direction that gets rid of that addition or replaces that loss. But no matter which one you look at, one of those four, a new equilibrium state, a new equilibrium position is achieved. So that means your equilibrium concentrations for each of your reactants or products is different, but it's going to end up in the same ratio that allows it to have the same Kc value. And that I cannot stress enough. The second one is changes in pressure. again, we're going to work with the same reaction. Now, pressure only affects gases, period, okay? And then it only affects gases where there's a change in the number of moles of gases that occur. So you want to go and look at your reaction and look at the change in moles. So on our reactant side, we've got 4 moles of gas. And on the product side, we've got 2 moles of gas. So we have a change, which means that the pressure, change in the effective pressure, will have an effect on this reaction. So if you increase the pressure, so if this was done in a container, right, we want to increase the pressure. So when we increase pressure, one way to do it is to decrease the volume within that container so that the gases have to be in a tighter area, and that is increasing that pressure. A lot of times they'll do this by inputting or taking out atmosphere from the container in which it's in. When you increase pressure, you're going to favor fewer molecules so that there's more space for the molecules that are in the reaction to move around. So in this particular reaction, we are going to favor our products because there's only 2 moles of products in this reaction versus 4 moles of reactants. When you decrease pressure, you're going to favor the side with more molecules because now there's more room for those molecules to be present. So in this reaction, you're going to favor your reactants. If you have an equal number of gas molecules on each side, it doesn't matter. Pressure has no effect on the equation. That's why it's probably best if you write how many moles of gas are on each side of the equation before you try to determine what factors could affect the equilibrium for that constant, for that reaction. And again, your ratio of your equilibrium concentrations will change, but the ratio they're at will not. So you will still have the Kc value. Now, one thing that's really tricky about pressure is when you tend to increase pressure, you tend to increase temperature too. It just happens to, they happen to coincide with each other for the most part. And so you have to keep in mind that we isolate pressure by itself and we don't think about temperature and how temperature could affect when you increase pressure. The third effect is actually a little bit more difficult, and it's a change in temperature. So you need to keep in mind that Kc is temperature dependent. That means that a change in temperature is going to have a change in your Kc value. So guess what? We're going to do a little recap on topic 5, energetics. Enthalpy changes, right? So when you have enthalpy changes going through, if you have delta H and it is negative, that value that you get is negative, you have an exothermic reaction. If you have a reaction where your delta H is positive, you have an endothermic reaction. Hopefully you guys remember that, and it hasn't been too long. So what you need to do is you need to determine what that delta H is for forward and reverse reactions. So if your forward reaction and your reverse reactions are equal and opposite, so if your forward reaction has a delta H value that is positive, then your reverse reaction is going to have a delta H that is negative of the same value. So if you have positive 100 kilojoules per mole, you have a negative 100 kilojoules per mole for the reverse reaction. All right, so we're going to look yet again at the same reaction. So you have to be given the delta H value, all right? And that way you know what delta H looks like. Now the forward reaction, that delta H is always going to be given to you for the forward reaction, just so you know. So that means the reverse reaction is going to be positive 93. So that can kind of get you ready. So if we look at what's given, the forward reaction, because it's negative 93 kilojoules per mole, it is exothermic. That means it is releasing heat to the system. All right, so the heat is going out. So if we have a system, the heat's going out. And you have to keep that in mind when we're talking about temperature. So if we increase the temperature of the reaction that's taking place, what's going to go on? Okay, so if we increase the temperature, more heat is being pumped in, right? So we have more heat being pumped in. You're going to favor the endothermic reaction. Increase favors endo. So which direction is the endo in this particular instance? It is the reverse reaction. So we're going to see more reactants occurring. If you decrease the reactant, or the temperature, sorry, that favors the exo. So in this particular instance, the forward reaction is exothermic, so you're going to favor your products. All right? Now, the problem we have to think about is if you decrease the temp too much. So in this instance, if as we're trying to make ammonia, we want to decrease that temperature to favor the products, because by decreasing the temperature, you're going to pump more temperature into it, right? Well, the reaction becomes too slow. And so then it becomes too economical to be a significant reaction. So you have to find a happy medium. And we're going to talk about that with some example industrial reactions that take place. So in an instance, if you're increasing a reaction to increase the rate, so you increase temperature to increase rate. Well, when you're increasing the temperature to increase the rate, you're going to increase the Kc for an endothermic reaction. You're going to decrease the Kc for an exothermic reaction. So for these type of problems, you really have to think about what is going on based on temperature movement, because you want to add and remove, right? So add, remove, and that is the whole concept, right? So if we're adding temperature, we want to remove the temperature. If we're removing heat, we want to add heat. And so you want to think of what that cycle looks like, right? So if we're going to be adding heat in, we need to get rid of the heat. So if we're adding heat in, we need to remove it, and we do that by doing an endothermic reaction, because an endothermic takes the heat in. If we're removing the heat, we want to replace the heat, which means we want to add more in. So if we remove the heat, we're going to add it, and that is the exothermic reaction. And so that little graphic right there helps me think about which direction, and I have to talk myself through that situation. And because temperature affects the movement of particles and literally how much can be made, it will change the value of that Kc. Lastly, a catalyst. As we know, a catalyst lowers the activation energy. Now, it lowers the activation energy for both the forward and the reverse reactions. Therefore, the rate of both reactions increase by the same amount. So if we draw an enthalpy level diagram, if we have our reactants, we have our products, we have our activation energy. Now, as we know, if we add a catalyst, it lowers that hump, right? And so if you think about it, the distance to that hump, so here's the EA for reactants, here is the EA for products, which is why endothermic reactions are so much harder to be natural, right? But as we change that by adding a catalyst, that amount of distance that has to be covered gets a lot smaller. And it gets smaller for both sides because both sides are affected. There's no effect on the equilibrium position whatsoever. It just helps speed up the attainment of the equilibrium state. So a catalyst only helps rate. It doesn't change the equilibrium concentrations of the reaction. It's just how fast do you actually get there. So this is just a table summarizing what happens. So concentration changes your equilibrium position, but does not change the value of Kc. Pressure will change the equilibrium position only if the number of gas molecules change in the reaction. but does not change the value of Kc. Temperature changes the equilibrium position, but it also changes the value of Kc because Kc is temperature dependent, because it changes how fast the molecules are moving and therefore lowers or puts more molecules have the ability to have successful collisions and all that kind of stuff, forcing it in one direction. And a catalyst has no effect on the equilibrium position, only the rate. And it has no effect on the Kc, again, only on the rate. So we're going to end this conversation on how does industry use this? What is the purpose behind equilibrium? Now, what I have read is you need to understand the application of Le Chatelier's principle to predict what effects temperature, pressure, and concentration will have on the position of equilibrium and the value of Kc. Specific details of any industrial processes are not required. They are just in this video to help you think through an example process that could be given to you. So all of the test questions I've seen based off equilibrium and rate have dealt with these three examples that I'm going to give you. So the goal of industry, of course, is to make money. And you're going to make money by having a lot of product, right? So they apply Le Chatelier's principle to push the reactions to the right and towards the products. And so this is actually an actively used concept in industry. What industry looks at is how much yield are you going to get and what rate are you going to get there. And when they're going to go through and do this, they want to look at the ideal mix. And they may have to compensate because they're going to do a cost-benefit analysis. To get the most yield, the rate may take too long. That's not beneficial cost-wise. And so they're going to meet in the middle. So the most bang for your buck, essentially. The first is the Haber process, and this is for the production of ammonia. We have seen this reaction plenty of times now. Hopefully you've seen it. But this is one of the most used reactions since the 1970s. And it changed a lot of industry, and it changed and saved millions, if not billions, of lives through the the Green Revolution with the use of fertilizers. So ammonia is used for fertilizers, plastics, refrigerants, and explosives. Okay, it's in fertilizers as ammonium nitrate, and it's in plastics as nylon. Just for your information. Because I have seen a question, what is the purpose of ammonia? So remember one of them, fertilizers. All right, so if we look at concentration, right? And so if we want to look at concentration, what's the best way to do it? Well, we are going to remove our product, right? Because if we remove the product, we need to replace that product. So it's going to add more product, right? Pushing the reaction in the forward direction, which then increases the yield. So they siphon out that NH3 as it's being made, pushing the reaction in one direction. Pressure. Well, we go from 4 moles to 2 moles. So we want to increase the pressure, right? And so the increasing pressure favors the forward reaction. And so we use high pressure. And I mean high pressure. We use 20,000 kPa or 200 atmospheres. It's insane. So it's slightly dangerous, hence the explosives. Temperature, because we have a value here, negative 93 kilojoules, because heat's being removed, right? Moving out of the system. So we need to add heat back in. So the forward reaction is exothermic. So it is favored at low temperatures so that it can keep replacing that heat. And so it'd push it forward to put heat back into the system because we're taking heat out of the system. Now the problem is, if you go to too low of temperatures, it takes too long to make the product to make it worth it. So it runs this reaction at 450 degrees Celsius, which still seems really high, but oh well. And they use a catalyst, right? And they want to use a catalyst to compensate for the moderate temperature that they have to use. Now, they use an iron catalyst, that has an aluminum and a magnesium mixture to it. And they've actually started to introduce a new one, which is ruthenium, because they actually have found that ruthenium decreases the energy requirement of the whole system and runs it a little bit more efficiently. So even though they're like, hey, we've got a catalyst, we know what we're doing, they're actually constantly researching better ways to do this process so that they can still make more money and the end result. The contact process is the production of sulfuric acid. We use sulfuric acid for, oddly enough, fertilizers, detergents, that doesn't seem safe, dyes, explosives, drugs, plastics. Didn't know sulfuric acid was used, and actually sulfuric acid is the #1 produced chemical in the world. You know, nice little tidbit of information. Now, the production of H2SO4 is done in 3 steps. First, we have to combust sulfur, and this is a forward-moving reaction only. Then, we oxidize that sulfur dioxide, that product. Now look here, this reaction actually runs at equilibrium. So this is the one we care about. Lastly, once we have that sulfur trioxide made, we put it through this like complicated situation. So sulfur trioxide is actually reacted with sulfuric acid, and it's a highly concentrated sulfuric acid, which makes this blend that then we react with water to make H2SO4. We use this route because a route in which you're reacting SO3 directly with H2O is explosive and really, really dangerous. So they use this medium of actually using concentrated sulfuric acid to make sulfuric acid. But yeah, that's what they do. So conditions, pressure. We can only look at equation 2. This is our rate determining step. All right, and so pressure, we have 3 moles, we have 2 moles. So we want to increase our pressure, okay? And we're going to increase it to 200 kPa. So not nearly as much as the production of ammonia, which is why ammonia plants are very dangerous. But temperature, well, we need to know the temperature of that reaction, and it is -196 kilojoules per mole. So extremely exothermic, right? So we want to decrease the temp. But because you decrease too much, the rate of reaction decreases. So we use a nice moderate temperature of 450 degrees Celsius. Because we have to use a nice moderate temperature, the catalyst we use is vanadium 5-oxide. To compensate for that moderate temperature we have to use. And so equation 2 is where we affect how much SO3 we make, and then how much of that SO3 is used in that third reaction to move forward. And so that's where we have to control the rate of this reaction. Lastly, methanol. So the production of methanol, here's the reaction. So we take carbon monoxide, react with hydrogen, and you get methanol. Who knew? So let's go through. We can't use concentration, and as you noticed on the previous one, because looking at what is being produced, you can use concentration, but it applies the same every time. Remove that reactant, or sorry, remove the product, replace the product. It's the same kind of concept. So we're going from 3 moles to 1 mole. So what do we want to do? We want to increase that pressure. Now depending, they'll use it vary from 5 to 10 times 10 to the 3rd kPa. It all depends. Well, temperature, it's exothermic. So we want to decrease the temperature. Now they use a cool 250 degrees Celsius in relation to the other two. Lastly, a catalyst, which is a very interesting catalyst. They use a copper, zinc oxide, aluminum oxide mixture to combat that higher temperature to increase the yield of methanol that we are going to produce.